Hi everyone, welcome to Induscon 2021 in the session Industry Applications 1. My name is Milena Faria, I'm the chair of the session, and Professor Flávio Buiochi is the co-chair. During the presentations, the questions and comments can be done via YouTube and delivered to the presenters. I hope this interaction can be successfully done. And in the first time, we are going to see all short videos from the session. Then the authors will be in the screen to answer them. Flávio, good morning.
Good morning, everyone.
So let's start this section and good luck to the authors.
Hello everyone, we are going to present our Induscon paper titled Analysis of Magnetohydrodynamic Behavior of the Flow of Conductive Fluid in Pipes for Industrial Applications. The paper concerns the problem of Mhd pipe flow. In this type of problem, there is an electrically conducting fluid flowing with velocity u along the pipe, and the pipe is in a region under the influence of an applied magnetic field B. In the Mhd pipe flow, the relative movement between the fluid and the applied magnetic field generates induced currents, which in turn reduce flow velocity by means of Lorentz forces. A problem of the previous works in literature covering this topic is that most of them assume an uniform magnetic field distribution, which is an idealization because such a field does not actually exist in the real world. In this work, we perform a 3D numerical analysis of the Mhd behavior of the laminar flow of a conducting fluid in a cylindrical pipe. The bidirectional coupling we just described is analyzed in this paper, that is, the influence of magnetic field on flow velocity and the other way around. And for the first time, the analysis considers different configurations of magnetic field in the pipe walls. Also, the magnetic field considered is applied by magnets, giving rise to a more realistic distribution of magnetic field compared to the uniform field usually assumed in literature. The methodology, here it is shown the geometry modeled in the paper. It is a cylindrical pipe with a diameter of 6 inches, length of 2.5 meters. Its walls are electrically insulated, and there are in the first 1.5 meter long section of the pipe, 6 magnets were placed in a circular manner around the duct. There are no magnets in the final 1 meter long section of the duct. The flow is fully developed with velocity of 2 meters per second. This geometry was numerically modeled with OpenFlow software, which solves the Mhd equations using the finite volume method. In those simulations, we varied the combination of orientations of magnetic fields and the intensity of magnetic fields. For each intensity of magnetic field, there is a different value of a parameter called Hartmann number. Briefly summarizing the results, we found that the analyzed effects are significant for the repulsive configuration of magnets and Hartmann number higher than 10. One of those effects is that the flow velocity was reduced up to 35%. Thank you very much.
Olá, eu sou Felipe de Souza Santos e eu irei apresentar o trabalho intitulado Análise comparativa do uso de pirômetros e termovisores em barreiras sanitárias para a triagem de pessoas febris. O objetivo desse trabalho é comparar os resultados de medida de temperatura obtidos pelo pirômetro e pelo termovisor. Foram medidas temperaturas na região do ouvido, do punho e da testa em 3 diferentes momentos. Após 15 minutos que os voluntários chegaram a uma sala climatizada a 24 graus Celsius, após os voluntários serem submetidos a uma corrida a ritmo de trote por 8 minutos e após os voluntários passarem por um período de 20 minutos de descanso no mesmo ambiente da climatização inicial. Ao realizar a medição de temperatura utilizando o pirômetro, nós marcamos alguns pontos na região da testa e dos punhos com o objetivo de analisar possíveis variações de temperaturas dentro de uma mesma região. Já com o termovisor, nós utilizamos o software FLIR Tools para demarcar as regiões de interesse da testa e do ouvido e assim obter a temperatura máxima dessas regiões. Em geral, as temperaturas registradas pelo termovisor ficaram mais próximas da temperatura real dos voluntários quando se comparado às temperaturas registradas pelo pirômetro. Podemos notar uma variação considerável de temperatura dentro das regiões analisadas pelo pirômetro, principalmente nos momentos após o exercício físico e após o descanso. Também vale notar que a região do ouvido foi a que apresentou a temperatura mais próxima da temperatura real dos voluntários. Já a região do punho foi a que apresentou os resultados mais distantes da temperatura real dos voluntários, chegando a ficar cerca de 16% mais baixa que a temperatura real. Portanto, podemos concluir que o pirômetro possui baixa repetibilidade, ou seja, seus resultados variam ao longo de diferentes medições. Isso acontece devido à variação de temperatura existente dentro da região analisada e à dificuldade de se garantir que o mesmo ponto da região será analisado todas as vezes. Também podemos concluir que o termovisor é o instrumento mais recomendado para se aferir a temperatura corporal e que essa aferição deve ser realizada preferencialmente na região do ouvido. Por fim, concluímos que a região do punho não é recomendada para se medir a temperatura corporal quando o objetivo for realizar uma triagem de pessoas febris, visto que a sua temperatura é significativamente mais baixa que a temperatura real da pessoa e, portanto, essa triagem apresentaria uma alta taxa de falsos negativos. Em nome de todos os autores desse trabalho, agradecemos o tempo e a atenção de todos e as organizações que tornaram esse projeto possível.
Hello, my name is Guilherme, and I will present the paper entitled Evaluation Real-Time Ethernet Performance Indicators for SERCOS 3 Networks. We are in 5 authors from 3 different universities. More and more products are being manufactured in a customized way to meet the demands of end consumers, always striving for quality optimization of resources, whether material, financial, or human, and also, of course, for efficiency. It's right to assume that data exchange between machines in general needs to be very precise, fast, and efficient. The modern industry is highly dependent on industrial communication protocols since they are a key part of Industry 4.0. Real-time Ethernet-based protocol accounts for 64% of it. Closing the scope of this work only in those protocols, it's possible to present 14 of them. The IEEE 61784 standard proposes 9 performance indicators. The scientific community suggests 2 more performance indicators being cycle time and jitter. This article aims to study a real network of an automotive plant as a function of its performance indicators. The chosen protocol is SERCOS 3 because there is a little research on it. In addition, a quantitative literature review will be carried out, and finally, the study for 4 performance indicators will be addressed. Starting with the quantitative bibliographic review, it's possible to verify that there is a tiny amount of work developed. The messages were collected from a real automotive plant using Ethernet top. It's possible to calculate throughput real time and non-real time. It is observed that they are relatively low. A pertinent analysis about the communication channels present in SERCOS 3 communication. The jitter of approximately 90 nanoseconds is relatively low by the modern industry standards. Considering the average jitters presented, it's possible to verify that Mhd messages from the primary channel present the best values. Another analysis to be done is in relation to the standard deviation, noting that the primary channels presented the best results. Industrial communication has been awakening both from great manufacturers of automation products as well from the scientific community. The discussion presented in this paper certainly are suitable for future works. The focus on SERCOS 3 network showing that this protocol has small jitters, which make it extremely suitable for environments with strict cycle times. The authors would like to thank you the funding agencies. Here are the references, and thank you very much.
Hi everyone, my name is Fernando Amaral. I am from the graduate program in Electrical Engineering from Universidade Federal de Minas Gerais in Brazil. Today I'm going to present for you the work entitled Increasing the Right to Fault Capability of a Power Electronics-Based Arc Flash Suppressor. Well, this work is inserted into the context of arc flash suppression in switchgears and motor control centers of commercial and industrial power systems. The objectives of the paper are to reduce the current to the suppressor and extinguish the fault safely at the same time. The scope is single-phase arcing faults, and the purpose is to include a series impedance into the suppressor branch right here, here, and here, since it's a three-phase solution, to reduce the current to the thyristors when the arc flash suppressor is turned on. The problem treated here is a transient nonlinear problem, and we used the sensitivity analysis to perform a case study on the worst case scenario. All the modeling was done via text in ATP draw. So the ATP draw model includes the thyristor, the arc flash model, and the power system model. A commercial device was modeled in ATP draw, as well as an arcing fault model obtained experimentally from IEEE and FPA research group. Here are the parameters of the test, and here is the comparison between experimental and simulation results for the waveforms of voltage, current, and conductance of the part. The results of the work have been divided into two parts. The first one refers to A to ground fault for many conditions, and the second one refers to A to B fault, again, for many conditions. The main findings of this work is that the worst case scenario is phase-to-phase fault, solid grounded neutral, the current limiting impedance with the same power factor angle of the power system, and the fault starting exactly at this angle in the voltage waveform. As future work to be presented in the next paper, we are obtaining experimental results from tests performed in a commercial switchgear. Thank you.
The title of this work is Identification of Pre-Stress and Degradation in Piezoelectric Transducers. The authors are Arnold and de Oliveira from School of Technology, Unicamp, Limeira, São Paulo, Brazil. In this figure, we see piezoelectric transducers and the respective schematic. Usually, the piezoelectric transducers employed in ultrasonic high-power applications are assembled with piezoelectric ceramics, metallic pieces, electrodes, and a central bolt. The central bolt tightens the transducer applying the pre-stress. Typically, this pre-stress is around dozens of megapascal. This action avoids fractures in the ceramics in the retroactive semicycle. Due to external factors, the value of the mechanical pre-stress can decrease. Changed pre-stress causes resonance shifting, as we can see in this figure, and as a consequence, we can have problems of impedance matching between the transducer and the driver circuit, and therefore this means less performance. In this work, we propose a circuit referred to as CTPS, Circuit to Test Pre-Stressing, able to check if the transducer is operating under the right level of pre-stress. This is the schematic of the circuit. The circuit operation is based on the detection of null phase between current and voltage across the transducer. The output voltage Vs is proportional to the phase and correlates the level of pre-stress. We have tested 3 transducers. The results were demonstrated a sensibility of 230 millivolts by megapascal. Therefore, our circuit could be an option to verify the level of pre-stress in piezoelectric transducers and guarantee the use of transducers under best performance. Thank you.
Hello everyone out there, my name is Zubair and I am the first author of this paper. The title of my paper is Copper Woven Sheet, a Novel Solution to Dissipate Static Charge in Electrical Machines. This paper is co-authored by Mr. Muhammad Ahmed and Mr. Muhammad Maslim. The fourth author is Dr. Ahmed Suhail, who supervised us in this paper, and last but not the least, Mr. Asghar Ali Rana. Moving on with the introduction, we know that industrial GDP, the industrial contribution to GDP is very important, about 30% global and, 20% in a developing country like Pakistan. And these, basically, these industries are majorly dependent on electromagnetic machines like generators and motors, because of their long duty hours. But the issue is, when they are continuously running at the RPM of 3,000 round, they build a static charge, and that static charge causes electrical breakdown in long run. So basically, this is because of the old techniques that are being used to ground these static charges, and they also cause occupational accidents. Around 2.3 million are affected every year, according to ILO. So this eventually leads to the revenue loss. For example, if the machine is stopped at, and there was certain production of, for example, fertilizer was going on, it certainly stops, and there's a production loss eventually. The old methods are carbon brush method, bristol brush method. Proposed method is the carbon brush, to discuss later. So first, in the carbon brush method, it is very short span. Basically, it's a sandwich like attached to the. For example, if this is a shaft, this is like attached like this. And also the second method, the bristol method is also like attached like this. Basically, both of them have very short lifespan, and need manual replacement after a few days, and it is very expensive, and that's why this is not certainly required. This is basically a comparison of both techniques. You can see, basically they work good till 9 days, 10 days, 11 days, then the graph start rising. Basically, the rising is of the rising of the voltage. At 178 voltage, there's a electrical breakdown that occurs, and the whole setup stops. Conductive microfibers method. In this one, basically, it is slightly better than the two because of the mechanically good shape and soft strands, frictionless. But it has also limitation that it is fixed with diameter. It has few months of lifespan. The machine runs for long hours and for many months, 6 years to 1 year. So this is not good for that. Other than that, it is expensive in long run, need manual replacement. It is not automated. This is the setup of a proposed technique. Basically, it's a motor shaft combination with a wheel. Wheel is basically a replica of industrial shaft for diameter comparison size. Basically, this is a zoomed in variant. There you can see we have our copper sheet wrapped around the wheel to dissipate the static charge. Moving on with the test setup, it was a replica of industrial shaft. Wheel was symbolic to the shaft of the industrial size. Motor specifications are given here, like it was a 1.1 kilowatt motor. Grounding value was of our laboratory was 0.4. 3,000 RPM was matched to the industry thing. And we had a programmable ELA, to pull the sheets on the both ends. A recording oscilloscope was used to record the charge buildup, and the most important thing, the copper woven sheet roll, the carbon brushes and the bristol brushes, and the base frame to accommodate all. Proposed technique was very good, is very good in this sense because, it has a very good area range coverage of 3 to 270 degrees. It is fully automated. This is time experience. You can run this with it as long as you want. There's according to the schedule plan. No bristles, so no noises, so maintain charge, restriction-less, it cost saving, effective, inexpensive, and 4 times less than the old methods. So basically in this graph, you can see, if we start running into the operation, there's a little bumps you can see here. Basically this is, when the voltage start rising due to the ineffectiveness of the sheet. There's the ELA. The role of ELA is basically it pulls the sheet on the shaft surface, basically. So, if voltage rising, you can pull the sheet, it gets back, and, it repeats like this for many days. Basically, we performed the setup for the experiment for 30 days. This is just a 6-day show up here. And the conclusion is that it is very cost effective, saves millions of US dollars, very negligible cost. No frequent maintenance is required. Self-sustaining system, independent of machine runtime. You can run it for as long as you want. It is noise free and no manual help is required.
So now we are back. I will ask all the authors to come here. So now we are going to start to do the questions. We have no questions from YouTube. And we are starting with the paper Analysis of Magnetohydrodynamic Behavior of the Flow of Conductive Fluid in Pipes for Industrial Applications. The presenter is Ramon Araújo from Federal University of Pará. Hi, Ramon. Congratulations to your work.
Hello. Thank you very much. I'm here ready to answer to any questions you guys might have about the work.
Yes, actually I have.
Let's get started.
Okay, so you performed the 3D computational simulation. I was wondering if you already started an experimental analysis in practice.
Yeah, like this work wasn't an anticipation that we have made to reproduce the results of measurements that are planned to be made in experiments in the final months of this year or in the next year. So we are already working on validating these results on measurements. That's what the initial motivation for this work.
Okay, great to know. Another question is, I saw that you have 2 effects, no? Okay, influence of magnetic field intensity and the influence of flow velocity, right?
Yep.
So these two effects significantly affect the repulsive configuration and not the attractive configuration. Why?
Yeah, because after this work was published, we analyzed the distribution of magnetic field compared to these two arrangements of magnets, and we found out that in the attractive configuration, there is some sort of canceling in the magnetic fields produced by the magnets. So the effect that we expect to see produced by the magnetic field, since those fields, they are not in a distribution that is suitable for those effects to appear. That's why those effects were pretty much negligible for the attractive configuration. So this was a good result, because when we are going to work on the measurements to reproduce these results, we will already discard the attractive configuration of magnets. We'll just work with the repulsive one, which was the configuration that produced the results of interest we were expecting. And those results have a lot of industrial applications. I don't know, we tried to make it clear in the paper, but this topic of magnetohydrodynamics, although it's not very common to find in scientific papers, it has a lot of industrial applications.
Yeah, but very nice, very interesting your work. Congratulations once again.
Thank you very much.
I don't know if the other authors or Flávio wants to do questions, or can we go to the next paper?
Next paper. Let's go to the second paper.
Okay. Okay, so let's proceed. The second paper is Comparative Analysis of the Use of Pyrometers and Thermometers in Sanitary Barriers for Screening Febrile People. Presenter Felipe de Souza Santos from Federal Institute of Espírito Santos. Espírito Santo. Hi, Felipe. Oh, he's not here. So I think we can go to the third paper.
Okay.
And I don't know if he's come here again. So the third paper is evaluating real-time Ethernet performance indicators for SERCOS 3 networks. I don't know if I pronounced correctly, SERCOS. Presenter is Guilherme Sestito from University of São Paulo. Hi, Guilherme. Congratulations.
Hi, Milena.
Did I pronounce correct?
I use pronounce SERCOS, but it's okay.
Okay.
Yeah, that's no problem.
I think that's really nice, because industrial communication network is fundamental for the connectivity demand of Industry 4.0. So your work is very interesting. And actually it's challenging this kind of communication. So the investigation of this protocol is very, very nice. So I have a question. Did you perform your testing in practical platform or just in the simulation?
Thank you for the question, Milena. You said correctly, industrial communication protocols are key of the Industrial 4.0 that nowadays is really, really common to say, you know, and this kind of research I used to do with real data. I used to work in my own business, and I had the opportunity to go in a real plant, automotive plant, let's say in this way, and I collected this. As we can see in my paper, this is a very, let's put it this way, this is a very simple paper, but this is really important because we figure out that we have some lack of this kind of research with this specific protocol. Okay, my expertise is in another protocols, for example, Profinet and EtherCAT or Ethernet IP, but this kind of SERCOS 3 protocol, this kind of protocol we don't have enough research on it. So,
actually, I was trying to search more about it because I didn't know. So I mean, I need to confess. So yes, there is not so much research regarding this kind of communication, but it's very nice. So if as far as understood, you did this in practical too.
yeah, I did. Yeah, it's a
Okay,
real.
That's difficult. But
Yes, it's difficult because I don't know if in other places are like this, but here in Brazil we are so worried about how to collect the data from the industry. You know, they are how can I say, worried about intrusion detection, something like this, or you can deliver this data for the other competitive player, you know. So
yeah.
I only had the opportunity to collect this data because I was doing a job for this automotive plant.
Oh,
Only
that's
for
nice.
that. Yeah.
Yeah, that's nice that you have this opportunity. Another question that I have is, do you compare these results with other protocols or not?
No, I don't. I didn't because they have some the dynamic of data exchange. You know, the data exchange, the communication are different. So it's difficult to compare between the 14 of them. But how can I say? I could compare in a major vision, you know, if they are inside the real-time Ethernet protocols, and we have 14 of them, and there are some
Specific requirements for each one
yes,
of them. Yeah, this is
yes.
the question, because if you did this in practice, that's really nice. That's really nice that you could go in the plant, in the system, and try to test this in a practical environment. So I was wondering, because this is difficult, and I know that there is some specific requirements to do this. And this is the question. So if you can compare this in practice, it would be very, very, very nice to see the throughput and other results. But I know that's very difficult.
Yeah, for sure. Yeah. And for example, for a Profinet that we have a lot of, I mean, my research group has a lot of papers on it. We are dealing with machine learning or data science, you know, to identify faults or some not good events on the network. So this paper is so important because it is the basis for future analysis like machine learning and data science.
Yeah, that's really nice. I like very much your work, and I need to study to read it, because actually I didn't know nothing about this protocol, but it was very nice, very nice.
It's so specific, yeah. But thank you for the questions.
I don't know if the authors have some questions, or Flávio. Do you want to do questions, or authors? We have nothing from YouTube, so we can go to the next paper, that is increasing the write-through fault capability of a power electronics-based arc flash suppressor. The presenter is Fernando Amaral from Federal University of Minas Gerais. Hi, Fernando.
Hello, everyone. Good morning.
Good morning.
Good morning. Milena, I have some question to him.
You can do him questions, no problem.
First, congratulations for your work, Fernando. I read your work, and I see you use a model to reduce the current through the suppressor. to safe extinguish the arcing fault. But could you go into more detail about the main contribution of this work?
Sure. This work is centered on a problem that is related to safety of persons and preservation of equipment of industrial facilities. So, on one hand, if we are not capable to extinguish the arc flash in a safe manner, we are not accomplishing our objective. On the other hand, the main solutions that are proposed in the literature to extinguish the arcing faults, they produce a parallel fault, an alternative path to the circulation of the current that was going to the arcing fault path. So we normally include a parallel path, and this parallel path it produces a bolted fault to the upstream equipment, circuit breakers, the cables, and etc. So we are proposing in this paper that we can include an impedance to this path, to this alternative path. So we reduce this current, the current produced by the arc flash suppressor, but this impedance cannot be higher than a certain limit, because if it's very high, the arc flash won't be extinguished. Okay, so we have a limit on one side and a limit and a limiting value on the other side. The main idea is related to this balance between a minimum value of impedance and a maximum value of impedance that we can insert into in the solution that we are treating in this kind of application.
Okay, Fernando, I suppose that the specification of the current limit and impedance determined by the model was used to compare the experimental result. Is that correct? Did you do these experimental tests?
Not yet. We are all the results that we presented in the paper. They came from simulations that have been performed into ATP draw, but the models that we used in our simulations, they came from experimental results. So the power system model, the thyristor model, the arc flash model, all of the parts that we use it to compose the simulation model in ATP draw, they came from experimental results that we took from based on other references.
Okay. How did you calculate the parameters used in the model? Is the solution found only in the time domain? The solution of the model in the time domain or the frequency domain?
No.
The parameters to determine.
The model has been executed only in the time domain, this discrete time domain. The problem is centered on a very short period of time. as soon as an arcing fault is detected, we have to control the power electronics based switch to eliminate the arcing fault. So the universe, the range of time that this work is centered around, is centered on, is a few cycles, a few milliseconds. Okay.
Yeah.
So there is it's more interesting to model the problem in the time domain, and I don't know if I can say it, but it's the only possibility.
Okay, it's correct. Okay, for me it's okay. Thanks for answering my question, Fernando.
I will take opportunity from one question that you did, Flávio. And once again, Fernando, congratulations on your work. So you said that this is just simulation results that you have, but your model is based on a physical system, right? So how difficult it is to do the experimental results?
Very, very, very difficult. We are working on a solution that is based that is applicable to a problem related to safety of persons. So we have to provoke an arcing fault in the lab, and to prove that our solution can eliminate this arcing fault, right? So we have to produce the fault itself. So we are working on having experimental results, and we have to do it step by step in a safely manner. So we are working on this phase of the project. We are preparing ourselves and the equipment in the lab, so we can produce experimental results in a safe manner.
I like very much your answer. You are preparing yourself.
Yeah.
But I imagine that is very difficult because when I was reading, I was like, wow, yeah, okay, you're basing this model in a physical system. So how can he do this on experimental practical analysis? Because you need to provoke this effect.
Yes.
So now you're in the stage of just to prepare the experimental results, right?
Yes, we are working on the experimental setup. The production of an arcing fault itself, it's dangerous because we have to take a thin copper wire, embrace it in a bus bar of switch gear or a motor control center, and energize it. So this thin copper wire will melt, and this way the arcing fault will start. So it's very dangerous to people
Yeah.
around the experiment.
And how can you guarantee this safety in your lab? You have some setup for this?
Yes, we have to initially to limit the maximum fault that we can obtain from our power system. So we are inserting reactors in series with the power system, so that if everything goes wrong, the incident energy that we have is very small.
Okay, so please take care of yourselves there.
Okay.
I don't know if the other authors have some questions. So can we go to the next paper, Flávio?
Yeah, okay.
Okay, so the next paper is entitled Identification of Mechanical Pre-Stressing Degradation in Piezoelectric Transducers. The presenter is Jaqueline de Oliveira from University of Campinas. Hi. Jaqueline.
Hi.
Congratulations from your work.
Thank you.
So I was wondering if there is any commercial device to identify the pre-stress variation.
In fact, there is a lot of systems or techniques to detect this kind of problem, but we are searching a way to improve this. So yes, and there's a lot of applications, just military applications or medical applications.
Okay, so we have some commercial devices, and did you compare your? I don't know if you compare these results, your outcomes, with this commercial or with some commercial device.
No. When I say this work is there is systems to track in the resonance of the transducer. I say there is a lot of techniques to detect the resonance tracking of the resonance of the transducer. So our work is another way to detect this. No, in our case, our system is to sorry, I'm kind of
Don't worry, take your time. I'm learning here. Everybody here is learning.
So there is some systems to do this, but our work is another way to do. It's kind of the. So no, there is no comparison to another works.
Okay. Yes, I was wondering this comparison, and your results is rely only in simulation.
Part of this work is simulation, and part not. And the part related to the mechanical pre-stressing was made in laboratory, the instrumental laboratory from the School of Technology, Unicamp. And with this and the
secret is in simulation, right?
The simulations, we have the results from this circuit, the development.
The operational amplifier.
Yes.
That you have. Okay, so but the schematic diagram of the load, this is in practice. You took the model from the physical test.
The model was physical test, and the results to the circuit was simulation.
Okay, that's very nice. This is very nice. So, what is the next step?
Well, the next step is do it the physical circuit in testing and physically in the laboratory, because physical is very different from simulation, and we have some problems with this in other works. So yes, the next step is make physical test in a laboratory.
Okay. Yeah, no, for sure. When we are doing the simulation, we are only expecting that the practical experiment will work at the first time. But we know that
in
is difficult.
simulation, it's everything beautiful.
Yeah. Okay, but don't worry. If it doesn't work in the first time, the second, the third will go right. Okay. What is the step now? The stage of the practical setup. We didn't this part yet. Just the simulation, or you already evaluating in the practical experiment.
Well, I have another work that is very similar to this work. And this circuit to detect the resonance tracking and PLL circuit and phase locked loop circuit, I already tested some circuit for that. So the next steps will be improve the circuit that I already tested in another work.
Okay, and which kind of you are going to use my controllers, right? Or just
Yes.
this? Yeah. What kind
Yes.
of one you are working with?
It's one the freedom at the freedom scale, and KL 25Z.
Okay.
There's a microcontroller. It's very good.
Okay.
Better than Arduino.
Okay, I note here the name. So thank you very much, Jacqueline.
Okay.
Congratulations. Don't be nervous. Flávio?
Jacqueline, yeah.
Yes, yes.
I think it supports your work, and it's a good job knowing the press stress is kept at a suitable level during the operation. It's interesting, and I'd like to know if could you use this circuit that you are developing when the transducer was in operation, or only after you turn off the operation, after the operation, before the operation, during operations. Sorry.
It's off operation. To this work, in this work is off operation. We tested the press stress on the transducer when it's not working. We can know we can know if they need some adjust on the bolt.
I asked this because the problem might appear during operation. I don't know if do you have an idea to develop a circuit to monitor the operation transducers together?
Well, what can I say?
But it's okay. You said now the test is off. When the operation is off.
When the operation is off, we can know with the bolt, the tight the transducer if he needs some adjust on the pressure on him.
Okay, now I understand.
Okay.
It's okay.
It's just that.
No, thank you very much.
All right.
It's interesting.
Thank you, Jaqueline. I don't know if the other authors have questions to Jaqueline or from YouTube. No, from YouTube, we have no questions. And the authors, someone wants to do a question. Okay, so we are going to proceed to the next paper entitled Copper Woven Sheet, a novel solution to dissipate static charge in electoral machine. The presenter is Huzaifa Zubai. I don't know if I pronounced corrected.
Yeah, it is Huzaifa Zubai.
Okay, you're a very nice person. Thank you.
Thank you very much.
So, someone wants to do a question, Flávio?
Okay, yeah, let's. About 6 presentation. Congratulations, Huzaifa.
Thank you very much.
Huzaifa,
no.
You can call me Zubair if it's fine.
You present a technique to dissipate static charges in electrical machines, saving sheet from breaking earlier. So experimental results you show were also presented to validate the proposed technique. So congratulations. Could you tell us what is the main advantage of this technique when compared to other techniques?
Can you repeat the question?
The main advantage of this technique.
Okay, so starting with the technique that I propose, it is better with the other technique because of the price thing. It is very inexpensive as compared to the other ones, and basically this is a big thing in engineering solutions when you're working on the industrial level. So after that, the breakdown problem, because the other techniques that that were in being used for decades, for 2 decades almost, it was copper woven, it was carbon brush method and crystal brush method. The problem is that they work till the 7th day or to around 2 weeks. After that, you have to replace the brush. You have to replace the crystals, in order to keep on dissipating the static charges that is getting developed on the shaft. So what we did in our paper is proposed a new technique. It's basically a sheet. In this sheet, there is no limitation of time. It is a timeless experience that I also said before. The reason is that it's like a tissue paper roll. For example, when you get it on the shaft, there is an electric linear actuator that is pulling it, which is basically programmed, according to the charge level. First of all, for example, when the voltage is rising at a certain level, for example, 7 volts is the set value for us because it was in our laboratory value. When the voltage exceeds the value of 7 volts, so basically, the actuator pulls the sheet on the shaft, and then the charge gets dissipated or basically you can say grounded. It can keep the charge level at a bearable level, which is required, 2-3 volts around voltage. So other techniques, the problem is that, in the old methods, after 7 days, after 8 days, they can work fine until 8 days or, 7 days, after 2 weeks. But after 2 weeks, the voltage start rising. The graph start rising, and at a certain level, there is a breakdown.
Okay. Do you have, I don't know if it's possible, a video to show us or a picture how the copper woven sheet moved around the shaft to use the linear actuator?
I don't exactly have video right now.
I didn't see in the article, I didn't see the linear actuator. How does the linear actuator hold the 2 ends of the copper sheet? Do you have a video?
I don't have exactly a picture right now, but I can explain it if you verbally. I don't have a big video right now. So basically, let's take the 2 ends of the sheet. Both are held by the linear actuator.
I can show your article I have here.
Yeah.
The picture, I don't know if it help you. What do you think?
Yeah, sure.
May I share your article?
Yeah, sure.
It's okay. Here. No. Sorry. Wait a minute. Compartilhar. No, it's not. Window. Now I find the window. It's here. Okay. It's your paper, so it's all right. I think it is the picture, no? Where is the actuator?
Yeah, this is the picture of the setup.
I'm going to...
There is actuator. I got your question.
No, sorry.
Yeah, I got your question. Actuator is actually not shown here because because of the space constraint. We just put up the model here. It's just fixed right now with the bolts right there. But eventually, in the long run experiments we did, there was an actuator used there. Like it's not shown here because as I said, there's a space constraint on the paper.
Shown.
But yeah, it's just the short sheet you can see here. The strip of the copper on the wheel.
Do you have an image with this that
Sorry?
you can share with us? An image that I don't know if I understand. Where is it?
No, this is the only thing I have right now because I'm really sorry because the material of my paper is in another laptop. So we.
Okay, no problem. No problem.
Yeah.
What are the specifications for this linear actuator?
What are the specifications?
Of the linear actuator? It's only, you said only a linear actuator, but what is it?
Sir, so basically
it's a
we use
piezoelectric actuator. It's mechanical. I don't know.
It's something like mechanical. For example, let me get into different parts. First of all, there was an electrostatic sensor that is deployed near the shaft where the charge is developing. Okay, once the sensor sends the charge, it gets the value to the linear actuator, and the actuator is programmed in such a way that when the voltage exceeds the value of 7 volts or 6 volts, it is taken as a high voltage, and which is not required. That's why the action of the actuator at that moment is it pulls the sheet on the shaft, and when the shaft is covered with the sheet, the value of voltage starts decreasing. And the linear actuator pulls at a certain level when the voltage is actually at a level of 1 volt or 2 volt, which is a bearable level, because we cannot let the voltage to exceed the value of 7 volts, which can be anything after that, because eventually when the voltage start rising, it at a value of around 170 volts, which is if we cannot ground at a certain time, the value of 170 volts gets in a few moments of time, which is not required. So that's why it is pulled over the sheet.
Okay.
I hope you get the answer.
You monitor the electric charge using electrostatic sensor. Could you tell us something about the electrostatic sensor? Where you put it? I think you didn't show in this picture.
Yeah, it's basically the simplest model. It was that we used there. So basically, the electrostatic sensor was deployed near the shaft, which is wheel in this case. You can see the wheel where the copper sheet is wrapped around it. So basically, it was around, a few centimeter distance between the wheel and the electrostatic sensor. It was sensing the charges basically that is developing there.
Okay.
And that was connected to the ELA.
Okay. Congratulations, Husaifa.
Thank you.
Good job.
Congratulations, Husaifa. Now I said correctly.
Yeah.
So this is a very interesting approach to solve and deal with this electrical breakdown problem. So I think that's very nice that you compared your proposed method with conventional methods. I think that's very nice, and you did this in practice. I was wondering the required frequency maintenance that you think that this proposed method needs, because I know that conventional methods you need to break all the setup, and so how what's the frequency maintenance that you think? I don't know if you have tests on this.
Frequency of the motor?
Maintenance, yes.
Yeah, it was around, if you can say, it was 3,000 RPM. So, you can just convert it. I don't know exactly how it will be going to frequency, but it was the speed of the, shaft that we were monitoring. It was 3,000 RPM. And why the reason was 3,000 RPM? Because when you go to the real industrial machines, for example, when there's a production of fertilizer is going on or any chemical going on, there the machine RPM is 3,000. So basically, we try to maintain that in our small scale model that we have, in the picture as well.
Okay. Okay. The other author, I think he had some connectivity problem, so he's not here. I don't know if some of the authors or Flávio wants to do a question to another paper. We can go back to the papers.
I don't know.
Can you hear me?
Yeah, please.
Yeah.
Yeah. So that was all. If you have any other question, I'm happy to answer it.
Okay, just I would like to do a question again to Ramon. Hi, Ramon.
Hi.
Okay. I was wondering here. You said that this magnetohydrodynamic is not so common. Can you give me some examples of applications?
Right. Some of the most common applications of MHD in industry is in the metallurgy industry, because with magnetic fields you can manipulate the flow, the velocity, and a lot of flow effects of conducting fluids. So people have been using those effects in the metallurgy. In the relaminarization of turbulent fluids, which is to reduce the velocity of a turbulent fluid to make it go back to a laminar state. It has some practical applications of interest in the industry. If we go outside the industry for a moment, just for curiosity, the MHD is the phenomenon that explains the magnetic field produced by stellar bodies like planets, stars. The most accepted theory for the Earth's magnetic field is the magnetohydrodynamic effect of the molten iron core inside of the Earth. So going back to industry, it was just for a curiosity. If you look at the industry, people have a lot of problems with pipelines, like. Depending on the type of fluid you transport inside a fluid, over time, this fluid might create some incrustations in the pipe. For example, over time, the free cross-section of the pipe starts to reduce because some parts of the fluid started to glue on the walls of the pipe, which the biological analog of that would be an arteria that is going to be have part of the cross-section filled by fat, which leads to a heart attack, for example. And an analog example of that happens in pipes. So it's not very established in literature, but a lot of papers, they have detected that you can use magnetic fields if the fluid is electrically conductive. Of course, you can use magnetic fields to reduce those incrustations in a very easy way, because you just need to insert some magnets around the duct, and then those undesirable effects, they go away, because if you reduce the flow velocity, this type of incrustation phenomenon, it tends to be reduced, right? So there are a lot of areas in the industry that people use the phenomenon. Another area that I can remember off the top of my head is that in nuclear reactors, in fusion nuclear reactors, I don't know if you guys know it, but those reactors, they contain a plasma that it is so hot that it cannot touch the surface of the reactor. So those guys, they use very strong magnetic fields to confine the very high temperature plasma inside of the reactor, so that the plasma does not touch the walls, right? So it has a lot of industrial applications. So our paper, we focused on the braking effect, which is like when you apply an external.
Oh, I think the connection.
Yeah, I can't hear. I can't hear.
I think Ramon had a problem with the connection. Okay, Ramon, I think you had some problem with the connection, but now you are back.
Okay, so that was it. I'm ready to answer some other questions if you guys have.
Actually, I didn't know. I didn't know this many applications that you can use.
Because like magnetohydrodynamics is like a very niche application. Few people work with that around the world. And it is like a field of study that combines fluid dynamics with electromagnetics, you know, like you use electromagnetic field to change the properties of the flow of conducting fluids. So that's basically what MHD is about.
Okay, so congratulations. This analysis, this behavior analysis, you can shift it from this kind of application to other applications, not only in industry.
Yep, pretty much. Like if you go back to the nuclear fusion power plant, it is going outside of the industry, for example, but the same effect of braking is being used in a very specific application, which is in power fusion nuclear reactors to manipulate an electrically conducting fluid. So you can adapt this application to many fields of it. You can apply this effect to many fields of application. It's very interesting.
Yeah, well, that's interesting, difficult, and for me totally new. So congratulations once again. I'm satisfied with your answer and all the answers of the authors. I think if you don't have any questions from YouTube or from the authors, we can end this section. What do you think, Flávio?
And second paper, Felipe didn't come back, no?
Yeah, so I think we can end this session.
Okay. Yeah, you can. We need to talk. I don't know if we continue in this session. You and I and me. I'd like to talk to you.
Okay. So we can end this session.
I think it's okay.
And we continue here. So thank you very much, Ramon, Jaqueline, Fernando, Guilherme, Josefa, was really nice for us to hear about your work. And I hope all of you can come again to Induscon in the next edition. So congratulations, and was nice to meet you all.
Thank you all for attending this virtual session, and have a nice day.
Thank you very much, guys.
Thank you.
Thank you, guys.
Thank you, everyone. Bye-bye.
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 Bye-bye.